Welcome to lecture 2.6. I think this aspect section of this session or subsession. It's going to be very short. I'm going to explain a little bit about, or give the definition of what the likelihood ratio test is. Okay, so. So this is in of your reading. It's on page 161 of Green. First thing that Green does is he defines lambda. This is a term he's going to use for the likelihood ratio test, and this is just the ratio. Okay, that's where it comes. What he's going to call L hat R and L hat U. Okay, where R means restricted, U means unrestricted. So what this is the likelihood under a restriction versus the likelihood when it's unrestricted. Okay, now what that means is restricted and unrestricted. Restricted means where your theory. So not your econometric theory, but like your microeconomic theory or game theory, or your political theory says something about what you should expect. And usually what it does, that will specify a null hypothesis. And then you can compute the likelihood when your model, when your likelihood function is restricted according to the null hypothesis. Okay, then you can also compute it when you haven't restricted. You allow all the parameters to just reach their maximum value. So here's what I mean by that. Here's an example. So in our toy example, where we have the probability that the country is going to select the largest party as formateur. One thing we might do is we could form a null hypothesis. I often call it H sub 0. And H sub 0 might be that, let's say that theta equals 0.15. For some reason, our theory said 0.15 is the magic number. It could have been anything, okay? But let's suppose that our political theory said that for some reason. And then usually we'll have an alternative hypothesis called H1, where theta is just not equal to 0.15. Okay, when this is the case, okay, now you have your spreadsheet where we could easily program in, we could easily compute this L hat R and L hat U. And specifically, here's what it would be. L hat restricted would just equal, if we went back to our spreadsheet and it computed, we computed the log of the likelihood, but it also, did I explicitly put a cell? I don't think I did, but we could easily do this. The value of the likelihood, not the likelihood, and this is L hat R, so L hat theta, where theta is just equal to 0.15. So it's what the restricted value is. So I think it was cell A6, just put in 0.15, compute the likelihood, L, and whatever that is, okay, that's our value that we're going to use for lambda. And then we would also want to compute L hat U, and in this case, this is just going to be L of theta hat. So you tell it, look, computer or whatever, find the maximum the theta that maximizes the likelihood function, and that's the unrestricted. We're not restricting theta at all. We're just saying let it be whatever you want. So once we do that, okay, then I'll go here. On page 161, page 161, it's theorem 4.20. 4.20. That theorem says that some smart people have proven this, that negative 2 times log of lambda, or that's lambda, that is distributed chi-squared with k degrees of freedom. Okay, and where k equals the number of restrictions. Okay, that's it, built into that L sub r. Okay, now you think, what does that mean? Well, for the first case, for this example, for our example of the formateur case, our null hypothesis only had one restriction. Okay, it said theta has to equal a particular value. There can be other cases, and especially when we go to a model where we're estimating much more parameters. And let me give you an example of this. Later on in the course, we're going to look at my and Jeff Milo's paper on media bias. And what we did is it's actually C. We computed the slant of different media outlets, and say media outlet J, we called the slant C sub J. Okay, that was a number between 0 and 100. And one thing we did is we computed 20 of them. So we had 20 media outlets in our sample, like Newsweek, Time, Wall Street Journal, NBC News, Nightly Report, and so on. So we had those 20 news outlets. So we had 20 CJs. Okay, so C1, C2, all the way to C20. Now, one natural hypothesis in this literature is that everything is controlled by the corporate parent. Okay, so at the time we looked at these 20 news outlets, and some of them had the same corporate parent, and I'm not going to remember which ones were which, but I think there was something like AOL Time Warner at the time owned CNN and also owned Time Magazine. Okay, so say CNN, say that was that news outlet 1, but instead of calling it 1, I'm just going to call it CNN. And say Time was news outlet 6, but instead of writing C sub 6, I'm just going to write C sub Time. And then there was also, at the time, the Wall Street Journal was, I think still is, owned by the News Corporation, which owns Fox News. And so that was one of our outlets, was Fox News Special Report. So under that theory that everything is dependent on the parent, the corporate parent, we would also say that the C, the slant of Fox, must equal the C of Wall Street Journal. I think those are the main two. We might have had 3 cases like that. NBC. I can't even think of it, but you can imagine other cases where we had 2 news outlets that had the same corporate parent, and we could have had 3 cases or 4 cases for this. So, but I think it was only 2, as I remember. So we had 20 different CJs, but under this theory, under the corporate parent theory, we're going to restrict two of the CJs to equal each other and two other CJs to equal each other. So what that means is we're actually going to estimate, instead of 20 CJs, we're going to estimate 18 because we're restricting C1 and C6 to be the same. Say Fox was C2 and Wall Street Journal was C7. I can't remember the exact numbers, but then C2 and C7 to equal the same. And so that means the other 16 could be anything, okay? So we're estimating those 16 plus 1, which must equal C1 and C6, and then another one which must be the same, C2 and C7 must equal. So what that means is we have two restrictions, okay? The other cases can be anything they want. So in this case, what we would call here, the K would be 2 in this case. So when I actually ran that, so in the appendix to our paper, we'll eventually get to that paper, I can show what the likelihood function is when we put in that restriction. So the likelihood function is going to be less, actually, than the unrestricted version. The question is, of course, it's going to be less, but by how much less was it, and was that statistically significant? Well, we can just use this formula to calculate whether that was statistically significant, whether, in essence, we can reject this null hypothesis, this kind of joint null. The null, in this case, involves two statements. Can't we? I think we did. I guess I remember. I think we did. We rejected this. Okay. So, that is a bit of a, this is going longer than I thought. This is a bit of a long-winded discussion what that K means. Okay. But in practice, I think usually the things you're going to look at, pretty much, usually, put it that way, K is just going to be 1. Okay. In a second, I'm going to give an example how we're going to actually estimate that. Now, what does the K mean? Now, one final thing before I go to the 2.7, lecture 2.7. Notice that we've got, we take lambda, then we take log of lambda, multiply it by -2. Okay, remember that the log of something is, wait. How is this log? Okay, let me go back. For a chi-square distribution, it looks something like this. So you should remember, if you take a normal random variable and you square it, the result should be distributed chi-squared, actually with 1 degree of freedom. So that means that the chi-squared, the value, that random variable, is going to go from 0 to possibly positive infinity. Okay, so it says it's restricted. There's no way, if it's a chi-square random variable, there's no way it can be less than 0. Okay, now, how have we built in that restriction, taking account of that restriction? And one thing I want you to see is that what that means is, so this thing has got to be positive, which means log of lambda has to be negative. Okay? Log of something is negative if and only if that lambda is less than 1. Okay? So this thing doesn't make sense if lambda is not less than 1. Okay? Will that be the case? Hit the pause button for a second. Try to think about that. Why it's got to be the case. Okay, if you're back, here's why. Here's why lambda has got to be less than 1. Okay. L hat U is the unrestricted version. Okay, that says pick the value of theta or whatever parameters that maximize the likelihood function. L hat R is pick the theta that might not maximize it, but maximizes it subject to some restrictions. So necessarily that L hat R will not be as big as L hat U. Okay, L hat U is what you do, how you maximize the likelihood function, subject to no restrictions. Okay, so for that reason, this thing has got to be less than or equal to that. So that means this whole thing has got to be less than or equal to 1. Okay, so that's why we can take care of that restriction. Okay, why this will always be meaningful. And by the way, so it means that if you've ever got a case where your value of -2 log lambda is negative, you've done something wrong. You haven't implemented the restrictions right. Okay, so that is 2.6. I'll come back, I'll say a little bit. In fact, I'm going to give an example of how to do that likelihood ratio test. So that we've just finished 2.6. I'll see you in 2.7.